In this problem, we're told that among the contestants in a competition, there are 46 women and 23 men. And 5 winners are randomly selected. We want to know what is the probability that they are all men. So off to the side, I'm going to list my group, which is 46 women, 23 men. And so that means that there are a total of 69 people. So we want to calculate the probability that all the winners are men. And we're selecting 5. And this is going to be without replacement. If we want to have 5 winners, then we need to be selecting different people each time. So, to calculate this, I'm going to look at what is the probability that the first winner is a man. So there are 23 men, and we divide that by the 69 total people. Then I'll multiply this by 22 over 68. That's the probability the second winner is a man. Because once we select the first one, that means that we have 22 men left and 68 total competitors. And then I keep going, reducing the number of men by 1 each time, and that reduces the total number of people. And then I get 20 over 66 and 19 over 65. So when I put that into the calculator, I get 0.00299 as my final answer. So a small probability that they would all be men. That makes sense because there's twice as many women as men. So that's how you do that problem. Let's take a look at question number 23. Here we have a study conducted at a certain college shows that 57% of the school's graduates find a job in their chosen field within a year after graduation. Okay, so the probability of finding a job is 57% or 0.57. And we want to find the probability that among 9 randomly selected graduates, at least one finds a job in their chosen field within a year of graduating. So we're calculating the probability of at least one finding a job. To calculate the probability of at least one, we're going to use the formula that the probability of at least one success is 1 minus the probability of no successes. So none find a job. Okay. So we've got a large number of graduates. We're not told how many there are, so we don't know the size of the group that we're sampling from. We just know that 57% find a job. So we are assuming that the group is so large that we can assume that this is with replacement, so that these trials are independent. So if 57% find a job, the probability of not finding a job is going to be 1 minus 0.57 for an individual, and that's 0.43. So I'll use that here in my calculation. 1 minus the probability that none find a job, so that means the first one does not find a job, and that's 0.43. And then we multiply that by the probability the second one does not, and that'll be another 0.43. And we keep going all the way up to 9. So I'm going to calculate 1 minus 0.43 to the power of 9. And when I do this, I get 0.999, and then it's 4 something, but it rounds to 0.999. So now let's take a look at the next question, number 24. Here it says a sample of 4 different calculators is randomly selected from a group containing 18 that are defective. So I'll write that down off to the side. And 40 that are not defective. And that means that there are a total of 58 calculators. Okay. I want to calculate the probability that at least one of the calculators is defective. So again, I look at the probability of at least one, and I say that's 1 minus the probability that none are defective. Now, in this case, we know how many calculators there are, and we're going to select 4 of them. And because we're selecting from a small group, relatively speaking, 58 calculators, so we'll need to select without replacement, and we're going to treat this very similar to what we did in number 22, that first problem we saw. So, probability the first one is not defective, well, that'll be 40 out of 58. And then the probability the next one is not defective, so now that'll be 39 out of 57. And then we keep reducing by 1 each time. And now 37 over 55. And when I pop that into the calculator, I get 0.785. And that's how you do that problem.